Hey everyone, and welcome. I am absolutely thrilled you're joining us for this explainer today. We are going to be unpacking the incredibly dynamic, basically nonstop interactions of physical forces that drive our weather, and crucially, how they directly impact aviation. If you've ever looked up at the sky and wondered, what exactly are the invisible mechanisms deciding whether your flight gets delayed or whether you need an umbrella? Well, you are in the exact right place. We're going to break down the grand atmospheric theater playing out right above our heads and see if we can make sense of the whole shebang together. I mean, really think about it. What turns a perfectly calm, beautiful sunny morning into a chaotic, turbulent storm in just a matter of hours? It can feel completely random, right? But the fascinating part is that it's actually a highly predictable physical struggle between colossal bodies of air. And once we know what to look for, I promise you, we'll never see a weather forecast the exact same way again. Okay, let's dive right into this. Here is our roadmap for today. We'll be covering 1. The forces that govern our airflow. 2. Air masses and frontal boundaries. 3. The formation of frontal fog. 4. Depressions and tropical cyclones. And finally, number 5, anticyclones and western disturbances. Starting off with Section 1, the forces that govern our airflow. First things first, we need to establish our baseline definitions. The main characters of our story today are air masses. An air mass is simply a massive, sprawling body of air that has relatively uniform temperature and moisture properties across its vast expanse. But the real drama? That happens when these giant bodies of air start moving. When two conflicting air masses collide, say a cold, really dry one and a warm, highly moist one, they absolutely don't just mix peacefully. They clash. And that battleground where they meet, that is what we call a front. So what's actually pushing these massive bubbles of air around the globe? Well, it's a really delicate balance of 3 primary forces. First up, the pressure gradient force, or PGF. Think of this as the engine. It drives wind directly from areas of high pressure over to areas of low pressure. But the Earth is spinning, which brings us to the Coriolis force. This acts like a planetary director, deflecting moving air to the right in the northern hemisphere and over to the left in the southern hemisphere. And finally, down near the ground, usually up to about 2,000 feet or so, we have friction. Friction actually slows the wind down, which in turn reduces that Coriolis deflection, allowing the surface winds to angle just a little bit inward toward the lower pressure. Moving right along to Section 2, air masses and frontal boundaries. This brings us to a really critical showdown, the cold front versus the warm front. And what's honestly fascinating here is how physically different these two boundaries are from one another. A cold front is dense, it's aggressive, and it is fast-moving. It has a super steep slope of about 1 to 50, meaning for every 50 miles horizontally, it rises 1 mile vertically. This extreme steepness triggers violent lifting, which leads to convective turbulence and severe wind shear. Now, a warm front, on the other hand, is the slow, sprawling counterpart. Warm, lighter air gently glides up over retreating cold air at a much shallower slope, more like 1 to 150. This gradual widespread lifting creates massive areas of fog and just continuous stable rain. When you really visualize a cold front, it's intense. Because the cold air is heavier and denser, it acts literally like a giant atmospheric snowplow. It aggressively wedges itself right underneath the warmer air mass, violently forcing that moist air upward. And that rapid, sudden vertical lift, that is exactly what creates those towering cumulonimbus clouds, the heavy driving rain and the severe turbulence that pilots spend pretty much all of their time trying to avoid. Let's jump into Section 3, the formation of frontal fog. Now picture the structure of a warm front. You've got all this rain falling from the warm air mass up high, cascading down into the cold, very stable air trapped down near the surface. When that warm rain falls, it actually evaporates into the colder air. And this evaporation adds a ton of moisture to the cold air, rapidly raising its dew point until the air becomes completely 100% saturated. The result? Massive, incredibly persistent banks of prefrontal fog. Because warm fronts move so sluggishly, these widespread areas of low visibility can just camp out over an airport for days, routinely wreaking havoc on flight schedules. And because of that shallow 1 to 150 slope we mentioned earlier, the cloud formation ahead of a warm front is incredibly structured. Seriously, it's like clockwork. If you are standing on the ground as a warm front is approaching, you are going to see a highly predictable, stratified sequence of clouds over a few days. First, the high, wispy cirrus clouds roll in. Then they sort of thicken up into a hazy cirrostratus layer. Next, the skies lower and turn gray with altostratus, until finally you are just under this thick,
dark blanket of nimbostratus clouds delivering that continuous, steady rain. It is a perfect textbook progression of atmospheric physics right in front of your eyes.
All right, Section 4, Depressions and Tropical Cyclones. Okay, so as these spinning low-pressure systems start to really intensify, they graduate through some escalating classifications. The absolute crucial takeaway here is how wind speed directly dictates the core aviation hazards. A basic low-pressure area, under 17 knots, might just bring some annoyingly low ceilings and light rain. But as the system deepens into a depression, pushing up to 27 knots, you get widespread stratiform clouds. Push it even further to a deep depression, up to 47 knots, and suddenly you're dealing with heavy rain and strong wind shear. Once it hits 48 knots and graduates to a cyclonic storm, we are talking about severe turbulence and torrential convective rain. So let's dissect the absolute extreme end of that scale, the tropical cycle. The structure of these storms is just fascinating. Right in the dead center, you have the eye, this deceptively calm area spanning about 10 to 30 kilometers with literally no clouds and practically calm winds. But immediately surrounding it is the inner hurricane core. This is the absolute most dangerous zone, featuring towering, dense wall clouds and winds just screaming between 64 and 112 knots. Beyond that, the outer hurricane core stretches out for about 400 kilometers with spiral clouds and heavy rain, finally fading out into the edge, where winds and cloud cover start to diminish. Now, here is a hugely practical takeaway, especially if you have an interest in flying. In the Northern Hemisphere, because of that Coriolis force we discussed earlier, deflecting the air to the right, low-pressure systems always spin anti-clockwise. Therefore, if you're flying directly towards a cyclone, the winds will always approach your aircraft from the left. And conversely, if you're flying away from it, the winds are going to strike from the right. It's a remarkably simple, brilliant rule of thumb born entirely out of our planet's rotation. Finally, Section 5, Anticyclones and Western Disturbances. So far, we focused really heavily on low-pressure, rising air. But what about high pressure? Well, anticyclones are regions of absolute stability. In these zones, the air is gently descending, which completely suppresses vertical cloud development. This gives us clear blue skies and light, calm winds. Sounds great, right? But don't let that fool you into thinking they're completely hazard-free. That exact combination of clear nighttime skies, light winds, and a super stable atmosphere is the perfect literal recipe for intense radiational cooling, which frequently traps really stubborn radiation fog right down at the surface. Now, let's shift gears and look at one of the most incredibly unique weather systems on the entire planet, the Western Disturbance. This is an extratropical cyclonic storm that usually forms way over in the Mediterranean. But then, it gets caught in the high-altitude, subtropical westerly jet stream and essentially rides it eastward all the way to the Indian subcontinent. It's an amazing journey. To the west of its core, it pulls down cold, dry air, creating massive areas of radiation fog. But to its east, it pulls warm, extremely moist air right up from the Arabian Sea, slamming it directly into the Himalayas. The real-world impacts of these Western disturbances represent an incredible double-edged sword. On the one hand, they are absolutely fundamentally crucial for regional water security. I mean, they bring the vast majority of winter rain and snow to the Indus and Ganges river basins. When that moist air is violently forced up the Himalayas, a process known as orographic ascent, it dumps heavy, vital snowfall. But because they are just so dynamic and so unstable, they can simultaneously trigger devastating extreme weather hazards. We're talking severe hailstorms, cloudbursts, flash floods, and deadly avalanches in the mountains, all while completely socking in airports to the west with deep, impenetrable radiation fog. Wow, okay, we have covered a tremendous amount of ground today, all the way from the micro forces of planetary spin to the colossal, continent-spanning storms that water our crops and delay our flights. Everything is connected in this massive, continuous physical struggle. So I'm going to leave you with this. The very next time you step outside and you feel a sudden, unexpected shift in the wind, or you feel the temperature suddenly drop, look up. Ask yourself, what invisible boundary just passed right over you? What epic act of the atmospheric theater is playing out right now? Thank you so much for exploring the skies with me today. Stay curious, keep learning, and I'll catch you in the next explainer.